image registration, and the question was, before we can do the image registration, we need to know correspondences. Okay, so let me give you a few cases and show you how do we determine the correspondences before we can align the two images. Okay, let's say you were dealing with some, rectangular type of objects, for example, integrated circuit chips, and you wanted to analyze, the circuitry in the two chips, whether somebody copied it or not, whether they are similar or not, right? Okay, so if this was taken, let's say, from an X-ray image, another one was taken, slightly smaller, maybe some time ago. So obviously, before we can do an accurate analysis, we need to align these, right? So in this case, the goal would be to see if we can come up with 3 or 4 correspondences. So easy way to do this would be through which technique? What technique that we have learned that lets us know these points?
Corner.
Yeah, what was the name of the algorithm?
Harris corner.
Harris corner detection. So you can apply a Harris corner detection over here. Still, there will be one small issue over there. Okay, let's say the Harris corner gives us 4 values over here, right? They will be x1, y1 for one of the corners, x2, y2, x3, y3, and x4, y4. Or let me call it prime. Okay, for this image we get x1, y1, x2, y2, the 4 corners over here, x3, y3, and x4, y4. Okay, so remember, for our correspondence to work, even though we know these are 4 corners, we have to make sure the left corner matches the left corner. So how would we know? For example, this point is similar to which one of these? Okay, for rectangular shapes, it's easy. What will be the left corner? Where xy has the... If you just compare all the x's and y's together, all the x's and all the y's, how would you know it's the left corner? What's the coordinate?
The lowest y value, right?
So lowest x, lowest y will give you, actually in this example, if you take a look at this y value is higher than this one, right? Sorry, this case it will work out okay, but what if I had it opposite?
Yeah, shift it up.
Like this. Then as you can see, so we can go by, for example, for its left corner, right? We can come up with a collective function so that sum of xy is smaller than, so if we did, for example, x1 bar plus y1 bar for this point, and if we did x1, whatever that is, x2 bar plus y2 bar, or x3, let's call this x2. Okay, which one will produce a lower value? This one will be lower sum than this one, right? Because the y value, as you can see, is pretty high over here. So anyway, all I'm trying to say is for rectangular shapes, establishing correspondences after we have detected the corners is not too difficult. We can come up with some kind of a simple or more sophisticated algorithm to say, oh, this point is out of these 4, this is the left corner. Out of these 4, this is the top right corner, and so on. Same thing over here. So then we can exactly match this to this, this to this, this to this, this to this, apply our transformation, and we will know how to register it with this one. Yes?
What if the image is exactly upside down?
True, there will be cases where it will not be as accurate, and this is where we're coming to the next technique. So regardless, this will work for simpler cases, but as was pointed out, may not work for all cases, right? Or what if this was a square type of image? Even if it is 90-degree rotated, it will not work, okay? So as you can see, what we need is, with every, let's call this a feature point. So will you agree this feature point, rather than just telling us X and Y, it should have also more information over here, right? For example, one of the information could be which way is it the surrounding, if we take a look at the surrounding pixels, which way are they oriented? Okay, are they oriented on average this way or on average this way? So then we can try to match the orientation as well to have a better idea. So as you will see in today's lecture, simply Harris corner detector is not a good approach. It is, I mean, once again, it will work for simpler cases, but not for more involved cases. So this is where we need SIFT or SURF.
Professor,
Yes.
what do you mean by orientation of the pixels?
If we, okay, the details are coming in today's lecture, but if somehow we can come up with an idea of an angle involved over here, okay? So one way to compute the angle would be, let's say,
Like the rotation angle of the picture, or?
no, we basically take a look at the region, we sum the pixels, and then take a look at the tan inverse. So it's slightly involved. As I come to today's lecture, you'll get a good idea. But bottom line I'm trying to say is that we all agree that simply knowing the location of the feature point doesn't help us, because then if you establish the wrong correspondence, meaning if you try to connect, assume this is actually corresponding to this point, it will totally mess up the registration.
Could you consider features like RGB for the pixel? Why don't correspond?
That could be more information, but anyway, wait a little bit more and then we can come back to it. What is that more information? Okay, so like I was saying, this more information is where the SIFT or SURF algorithm comes into play. Okay, SIFT was the original pioneering algorithm in this particular domain. Scale invariant, so it stands for scale invariant feature transform. Okay, then whoever I think was developed by somebody in Canada, it became very famous algorithm, and the person patented it. So like I was explaining, they put it in OpenCV, but because they have a patent, and the whole idea of OpenCV is, it's open to everybody. So then they had to remove it, right? So then one downside of this algorithm was it's slow. As we go through the details of it, you'll see why it was slow. And so then this algorithm came up, which is called speeded up. I forgot what R was, speeded up. Anyway, features or something. Speeded up robust features. Okay, so basically they improved this algorithm, made it faster, but then whoever developed it also patented it. Okay, so this also disappeared from OpenCV. So our choice these days, there are a couple of algorithms. One is ORB, and there's a few others in OpenCV. For your assignment, you'll be dealing with ORB, and I'll show you how to program it and how to use it. But anyway, first before we go into the details of the algorithm, let's try to see what's the purpose over here, okay? So the purpose is like this. Okay, suppose I gave you 2 images. And let's pick a car as an example. Okay, and here's another picture of the car, but was taken by different cameras, maybe different day, different background. Okay, so how do we establish correspondences between these? And as we discussed, not only we want to know, for example, this point matches this point, we also want to know not just the XY location, but also some more information about it, like rotation, maybe which way the gradients are, and so on, okay? So if we can detect, let's say 7, 8 correspondences, like this, right? And so on, then we can register the 2 images, and later on I'll also show you a concept called homography, which has some very interesting applications. Then we can also develop a homography matrix to stitch the 2 images. Just to give you a very brief idea, let's say you took a picture of a mountain range or something, right? Your camera only captured this much image. You took one more picture oriented this way, so you captured. So these are 2 separate images. Now we want to basically stitch them together so that we can recreate a panoramic view. So again, this is where the homography matrix comes in. But here also, we need to know the correspondences between the 2 images. Okay. So, okay. So anyway, you could still argue even for a car. Okay, maybe the corners can be easily detected with a Harris-like algorithm. And why do we need a more sophisticated algorithm, right? But what if it is like some butterfly, you know, you were a biologist in this scene. Okay, here the butterfly is somewhere here, could be the same, could be different, and we wanted to register the butterfly. Now pretend these are all rounded things. How would we know what's the correspondence between the 2 before we can identify the butterfly as an example, right? So, so we need features. So we need features, meaning points of interest on a butterfly here, so that we can establish the correspondences, okay, that are scale independent, meaning whether, see, this picture might have been taken far away, this picture is a little bit closer. So if we wanted to detect the wing on some point on a wing on the butterfly, same thing over here, regardless how far or hard, even if the butterfly turns, okay, this point should still be recognized as, you know, the exact same point on the other image. So they should also be rotation independent. Okay, anyway, so that was the idea behind SIFT and SURF. So now let's go into a little bit detail of the algorithm. Like I said, both SIFT and SURF are extremely complicated algorithms. Our goal is to at least get a good understanding of how the algorithm works. We won't program it from scratch, because if we programmed it from scratch, we'll be here next whole month programming it. We have to learn quite a few things. So after we learn how internally it works, we'll just use the OpenCV library, the ORB, to establish the correspondences, compute the homography, or compute the affine transformation that we discussed in your last assignment, so that we can register the 2 images. Okay. Okay, before I go and show you the details of the sift and surf algorithm. Couple of small concepts. Okay, which are pretty commonly used in computer vision. The first concept is called integral image. Okay, so integral image is computed like this. Okay, let's say we have an image, and to make it easier, let's take a look at grayscale. So pixel values are 50, 40, 10, 20, let me make it 60, 30, 80, 20, 40, 70, 10, 20, 10, 60, 50, one more, let's say 30, 50, 20, 10, 40, okay, and so on. So let's say this is how the pixel values are. Okay, so this is some image I, okay, we call it IMG. Okay, if we make it IMG integral, so this is not the integral in terms of, doing the mathematical integration. This is the integral over here basically means cumulative sum. Okay, so the way integral image is computed is, okay, at any point I of x, y, it basically gives us the sum of pixels up to that x and up to that y. Okay, so for example, this is the very first one, it stays 50, right? If I go up to over here, this position will be the sum of 50 and 40, 90. Okay, if I go to up here, this will be 50 plus 40 plus 10, 100. And you get the idea. Let's go over here, what will this be?
110.
80.
From the original. Yeah.
50 plus, right? What will be at this point?
120.
50 plus 40 plus 30, 80, 120, 200. Is that right?
Can you point again how you're going for the second
Okay.
row? So 50.
Basically, the sum of the pixels,
Okay.
if I'm putting this value over here, it's 80 plus 40, 120, 170, 30, 200, right?
Mm-hmm.
Okay, so anyway, and let me pick, for example, this value over here.
80, 20, 20.
So what will this be?
130.
That should be more, right?
Is that
90.
entire square,
Oh,
right?
that-
Yeah, the entire thing up to this
The
one.
3 by 3, so that.
Yeah, so this is 100.
206.
Then this is 130, so that makes it 230 and 270, am I right?
Yep.
Okay, so this is how we'll compute the integral image, okay? So why are we computing the integral image? Let me give you the benefit of this. One of the things that we use quite often in computer vision applications is called Hart transform. Okay, Hart transform is extremely easy. These are basically box filters. Okay, for example, one of the filters may look like this. Okay, so let me make it dark. So basically what it means is add all the pixels in the white region, subtract it from all the sum of the pixels in the black region. Okay, so let's pretend to compute this Hart transform. Okay, so if this is our image, okay, let's say we were interested in finding out what is the sum of pixels just in this box, right? So if you take a look over here, suppose I call this point A, B, C, D. right? Okay. And pretend this is the integral image. So we've already computed the integral image. From this integral image, our goal is to find the sum of pixels in this box called ABCD. Okay, so how will we compute it? If I take a look at the value I of B, right, what will that contain? Won't that contain all of this blue region over here? Correct? All of this blue will be I of D.
Yeah.
Do you agree? Okay. Now from here, if I subtract I of B, so then what will be left? So this is gone. So only this rectangle will be, because I of B is basically this blue that I drew, right?
Yeah.
And if I further subtract minus I of C,
Then here,
then what will happen?
end up with a summation we want.
However, what did we do to this I of A then?
Double.
We did it double. So what should we do over here?
Add it.
Plus I of A. So this will be the sum of the pixels in A, B, C, D region. So you can see if the integral image has already been computed, how many calculations we need to do to find the sum of these pixels? 3 additions, correct? And we are done. Regardless, we have 10,000 pixels in this region.
Oh, yeah.
So you'll see after the integral image, everything becomes extremely fast. So you will see this concept of integral images quite a bit in computer vision. Okay. So now let me take an example. Let's say we also have a region A, B, C, D, E, F. Okay, and your goal was, and let me make this dark. So your goal was basically you wanted to create a Haar feature. Okay, such that the sum of pixels in C, D, E, F is subtracted from sum of pixels in A, B, C, D region. Okay, in the end, regardless how many pixels are there, whether there are 10,000 pixels or 100 pixels or 5 pixels, doesn't matter. Okay, if we do this computation, what will we end up with? A matrix or just a number?
A number.
A number, because this is a number, this is a number, we subtract. So that's what we call a Haar feature as an example. Okay. So anyway, coming back to your question about an angle, okay? Because this is a number, this is a number. If I did tan inverse of this divided by this, it will give me some angle, right? So that could be considered whatever that angle is, as an example, the rotation of the data at this particular point, at the center point as an example. Okay, so that's how we compute okay, anyway, let's briefly take a look at how will we accomplish this, okay? Sum of pixels CD plus, wouldn't this be IF minus IE, right? Minus ID
I see.
plus IC, right? And minus, we already have this over here. So in just 6-7 computations, we will know the Haar feature, okay? So from correspondence points of view, if speed is important, Haar features will be one of our go-to techniques to give us more information about the actual correspondence point that we have located, right? So that's one concept, the integral image and the computing the hard features. And other concept that we will need to understand the sift and surf. Okay, what is a good feature? Okay, so to identify what is a good feature, right? You already have some idea. Do corners make a good feature? Yeah, they do, because they are distinct, right? Same way, you know, but like we discussed, if we have a butterfly, then, you know, if everything is rounded, we still want to know, is there something important over here or not? Okay. Especially if there are patches on the butterfly, as an example. What will happen to the gradient? We've already talked about gradient filters, right? If there's a patch over here on the butterfly, a patch over here,
Increase.
the gradient will increase, right? So typically what we do is we use LOG filters. You guys remember G for?
Gaussian.
Gaussian.
Low pass.
Laplacian of Gaussian. Okay, so let's think about it. How is this going to give us decent features as an example? What's the purpose of the Gaussian?
Reduce or
Yes.
reduce noise or
Reduce noise, exactly. Because see, there could be through the camera lens or whatever, or you know, some mosquito flying or whatever, you know, that's basically noise to us. So basically this filters noise. It's a low pass filter, correct? Okay, so first we try to eliminate the noise. Hey, what does the Laplacian do? Was it a first order derivative filter, or it was a second order derivative filter? Second order, right? So it basically magnifies anytime there's a change, it will enhance it even further. Okay, so to summarize, what I'm trying to say is, given an image, like a butterfly or whatever, we will apply Laplacian of Gaussian, and then take a look at, in this one, where the magnitude is the highest. So we can come up with some kind of a threshold. Any place where the gradient produces a high value, most likely some change is occurring. So that will be the point of interest, right? Okay, so to summarize, if you have to get an overall idea of the SIFT, SURF, or B type of algorithms, they basically go in 3 steps. Okay, step 1, apply LOG and put some kind of a threshold on it as an example to get initial idea of the features. Okay, so get initial features. Right? Hopefully this makes sense, right? Okay, after we have the initial features, okay, what if the butterfly was turned one way or the other? We want those features which still can be identified regardless which way the butterfly is turned. Okay, so filter out scale invariant. Or I should say keep scale invariant features, not opposite of that. Keep scale invariant features. So, and let me come to and third part is the rotation. Keep rotation invariant features. Okay, and then create a descriptor with the feature. Okay, so this descriptor is that more info that I talked about. So we'll have additional information about not just the point. So see on a butterfly, okay, we know this is a feature, right? As an example, let's say there was another image of a butterfly. Okay, let me make it similar. Okay, what's our goal? Our goal is to be able to establish correspondence, right? So what do we want? We want this to be only tied to this point, not any other point. If we only had the XY location, it doesn't give us any clue. This also has an XY, and somebody else has an XY. But let's say there was another set of 64 numbers over here, identifying, in addition to XY, more information over here. What is that information? We'll go into the detail in a minute. Then, once we did the sift or surf, this will also give us the 64 numbers. Okay, this will have its own 64 numbers over here. But these 64 numbers will be different from these 64 numbers. So how will we know that this point, so how will we pick the correspondence? If you're given 64-bit numbers, you're given another set of many 64-bit numbers. How will you know which one it corresponds to? They won't be exactly the same.
Can you ask again?
Okay, or let me make it even simpler. If I gave you just 2 points, two pieces of information, let's say 1.2.
Can it like mu and sigma? Something
Okay.
like this.
Yeah, that's one possibility. Okay, and suppose now, so this is one feature. So this is one feature. It has 2 identifiers, 2 numbers. Now, in the second image, we have, let's say, 8 features. 0.3, 0.7, 1.8, 0.9, 0.9, 0.7, 0.1, 0.5. So my question to you is, if we know we have to match this to one of these, what technique will you use to figure out which one is the closest?
Maximum of that.
Mu sigma correlation.
Correlation is one idea, mean squared error is another idea, right? So if we did the mean squared error, 0.9 minus 1.2 squared plus 0.7 minus 0.8 squared, it will give us, you know, a number which is smaller than all the others. So if whoever is the smallest is the closest match, right?